Здравствуйте.
Привет. I'm sorry because I was late, but I'll start in 2 minutes, I guess. Okay, let's start now. Do you have some questions, probably?
Yes, about the homework. Is it possible to ask?
Yes, okay, let's discuss it.
Thank you. About the third task.
Yes. This?
Yes, that one. Yeah, the problem is with the results of ridge and LS models. Even in the text, it is said that it is tricky. There are could be some problems. Could I demonstrate my screen?
Yes, I guess.
It is not allowed. Yeah. Okay, can you see the screen?
Yes.
Okay, so here's what I decided to do. I decided to use this class as it is said, but I don't clearly understand how it works as I give there the original model, then I give the parameters of ridge because those parameters are already built in the model. Let me show you the previous one. So here's the model I built, the linear one, usual one. Then I build a ridge and lasso one using the this method fit regularized. I just googled for it. There was no such in the seminars, if I'm not mistaken. So then I predicted it. Well, that already doesn't matter. So the thing is that I decided to use this class. And in case I try to use like this, there is an exception. Let me show you this one. It means that it doesn't fit here. Why is that? So why should I give the original model there? I don't clearly understand that.
I guess. As I remember what I saw on Stack Overflow, that people described how to fix this problem. They proposed to just make a new linear regression model, but pass to it the parameters from ridge, for example. So you train at first your regularized regression, then get parameters from it and pass it to a common model. So this model won't be training. It just use the weights that you passed, and then you can get less results.
And one more question about this parameter, about normalized covariance parameters. In case I don't give it to the method, there is also an exception that summary 2 can, well, okay, let me show you this. Here's the exception, yeah. Need covariance of parameters for computing. Well, if I'm not mistaken, it's about the second summary. So why else do I need to give that parameter? What is it?
Actually, is it stated as covariance of of parameters? Okay, I guess it's about the fact that okay, it's try to measure the uncertainty in your parameters. So of course, it try to calculate the covariance or dispersion or okay, I mean okay, or variance. So and as this a statistic method, it try to it need to know how your parameters are distributed.
But can't the method get it out of this model FGF as I just there are already parameters and I just give them in the method. Why can't this method use the parameters of the object I give?
I'm not sure. I guess it's how it's built, actually.
Okay, thank you very much. That's actually all of my questions.
Let's then go back to seminar, I guess. So today we'll discuss again classification, but today we'll try at first classification of texts, and then we will go to multi-class classification and SVM. But at first we'll discuss processing of texts. So I guess it's a rather fun topic. And the name of the methods that are used for analyzing of the text is usually it's named natural language processing or NLP, like in psychology. But it's actually another thing. So what we can do using natural language processing, we can have some texts and transform them to a view that our computer can understand. As a computer can process your text, you need to transform your text to some numbers or some vectors, and we'll do it now. Okay, let's import some libraries at first. We don't have a lot of new, I guess. We have again NumPy, pandas, and Sabon, and so on. Also, we have some libraries for classification. Also, we use TQDM. It's a very good thing that helps you to show some processing bars, progression bars like this. We will see it next. And now we'll analyze some data from Kaggle. We're going to do sentiment analysis. It means that we try to check is some text about some positive thing or negative or probably neutral. So we have a lot of news like this. We have, of course, we have train and test data set. And we try to predict the sentiment of all news. And also we have it in JSON format, so we'll need to process it somehow at first. Let's load our data. And here we can see that we not just open this file, we also use some function JSON load. It means that we just process our file as JSON to some to some variable. So we can see, I guess, it here. Probably. Okay. Probably it wasn't a good idea because this one is very big. Okay, but we can see it here. So what we have some ideas. It's idea of the news, some sentiment. So we can say that it's a neutral news, and some text that we have here. Actually, we have, despite the fact that we talk in English today, but the news are in Russian. And let's analyze it. So our task is actually a 3-class classification problem. We have 3 classes: positive, negative, and neutral. Let's look again on our data. So we have again ID, text, and sentiment. We can look closer on our text. So we can see that it's something about some criminal, I guess. And we have some information about it, so it's probably negative news. Let's go. So what we need to do with our text? We need to transform it to some vectors. But actually, the first thing that we need to do is to split our text to some smaller parts. How we can do it? We can split it to sentences, to words, or even to characters. But actually, if we split it to characters, it's probably not so good, as we can lose the structure of our words. And our computers are not so smart to understand how words should be built. So probably it's better to split it to words, at least. So we'll split our text to words. It named actually tokenization, as we and our words are here are tokens, or it could be our sentences, or probably characters. Another thing that we need to do, we need probably to remove our punctuation, as there aren't a lot of meaning in it. And also need to remove some words that are too common. For example, like these words. So it's probably some. So it's just the words that are firstly too short, and secondly, they are too common for our text, and they are not very doesn't bring a lot of meaning. So we use a popular library named NLTK, named also Natural Language Toolkit. It's very popular, but actually we should remember that this library is suitable for a lot of languages and also for Russian. But of course, as it's a multi-language model, it can be not be the best for particular language. So probably you should go for libraries that are built especially for some language. But of course, it's not the case for English, as the most part of libraries for text processing are, of course, for English. And it's also the same for NLTK. So let's download stop words, like the most two popular words in this language. As we work with Russian, we will use Russian stop words, and we can see them here. So there are some stop words. Also, we need to remove our punctuation. So let's see what punctuation is here. So there are some characters here. Next, we'll define our tokenizer, the function that can separate, they can split our text to words. Actually, in LTK, there are a lot of tokenizers, and this tokenizer can split our text to not only to words but also to some characters that are not words. So we can split also to numbers. So, for example, as we can see from docstring, no, probably not. Okay, let's see it in documentation, I guess. So some tokenizers in LTK can split only to words, and some can split also to different types of words and also to characters, like here. So we have this text, and if you process it, we can have it like this. To do wrong. Sorry. Okay, if we look on this type of tokenizer, word and punct tokenizer, so we can see that it separates all type of characters. So it separates actually this character from this. And if we take another tokenizer that is not suitable for punctuation, it doesn't separate actually, for example, numbers from points. So I just wanted to say that we should choose tokenizers that are suitable for our problem. But here we decided to just to split it, the text like this. So what we do here, we wrote some function for text processing. So we just go through our data, through our text, and firstly we try to make our words, to transform our words to lowercase. Next, we'll tokenize, split our text to words, and next we will remove all the stop words from our text. So we trace through our words, and if these words actually some punctuation, or if these words are in stop words, we will just remove them. And also we remove here dates. Actually dates, it's actually the year. I'm not sure why they do it, but I guess they thought that it's not very important information here, but also we have some probably important numbers as like this. It's the number of an article, of criminal article. So these numbers can be important for separating negative news and neutral news. So after this, we will just append all these tokens to some list. Then let's see what we have. So we run processing of the data. We also brought all our targets to y, and we can look at the example. So after processing, we have separate words, not text. So we have separate tokens like this, and we don't see any stop words since we removed them. Next step that we should do is actually some normalization of our words. We can see that there are different type of words, and probably there's a bit too much actually, especially in Russian, since we have a lot of different morphological forms of a lot of our words, but probably they bring the same meaning, probably not the same, but close meaning. So we will try to normalize our words, so the number will be not so big. To do it, we can use one of techniques. There are actually the two techniques that we can use. The first is stemming. Actually, it's just actually it's a very old technique. We just remove from word everything that can be not suitable for our task. We just, if we, for example, if we look at some word, we just remove all the prefix, all the suffix, everything that can be not important, and just return something that is similar to the root of the word, but it can be not it. Since stemming, it's just doesn't look on morphological structure of the word, so it's just a simple set of rules that transform all the words that they see. So they just remove from the word everything that is that can be not informative. And demmetization is actually a completely another technique. Here we use morphological structure of the word, and also try to check what is the part of speech of this word, and if it try to convert the word to its normal form and save the part of speech. So for example, we can see it here. So stemming just lost the last character, and demmetization saved it. So in demmetization we got normal word, and in stemming we got something a bit strange. But actually, it's not probably not very important in a lot of tasks, since we transform all the words to these small versions. So, and for computer, it's not very important other words right for our language, or they are not. So if we use, so if computer looks on a text, it should only see the similar words in the text. It's not very important if they are a bit broke like this. So stemming is also a good technique, but probably not for Russian language, but we will see it later. So how to do, for example, stemming? Again, we use NLTK. We'll use snowball stemmer, and also we will use lematizer, and we'll see how it works. Also, we need NLTK needs to load something for this library, and we will define our stemmer and lematizer. We also can define here the language, so it will be more suitable for the chosen language. And we'll see some examples. For example, in English, we have, so for example, if we use English language, we can see that actually stemming is not so bad technique. But for example, for this word universities, you can see that stemming just transformed to much smaller form that it should be. So the demmetization just saved university from degrading, I guess, to universe. But for some words, like for example carrot, stemming just turned a smaller word, but actually it's rather normal. Demmetization here, for example, saved the part of speech. So it's the same word. And for example, for this adjective, we can see that semi-returned the strange form, but actually it's one of the rules of the stemming, of this stemmer. So it just transforms all the adjectives with this suffix to this. I'm not sure why, but it's actually standard. And limitation saved the word again, and also the same. And also we can see the stemming was reduced to stem here, but in limitation we have the same word. So we can clearly see that there are some differences, but the more interesting thing that when you use your limitizer, you can pass here the part of speech. So for example, if you use the word better, we can say that it's, for example, some noun that the limitizer is just don't know. So it will just save this word since the limitizer thinks that it's similar to some noun. So it shouldn't be transformed to some form since we don't have, for example, s in the end or something like this. But actually, if we say this adjective, if you pass here a, then limitizer will understand that it should transform it somehow and transform it to word good. So limitizer actually, if limitizer understand which part of speech is the word, then it can return different results actually. So like this. Then let's see what's going with Russian language. If we again use stemmer, but now for Russian, we'll see it that actually all words are much different from how they are in the language. For example, we can see that we have some verb, and then we have a bit broked word, since it lost two last characters, and other words are also a bit strange after stemming. So we can see that for Russian probably stemming is a bit too much, just because in Russian we have much harder morphological structure than in English, and in English, for example, much more important is the structure of your sentence, and the morphological structure is not so much so complicated. So, and for languages where you know that morphological structure is complicated, like in Russian, you probably should use lemmatization, not the stemming. So again, if you pass here some sentence again to stemmer, we can have this bit degraded sentence, but actually it saves all the roots and sometimes a bit some other characters. But if we use limitizer, we'll have much better results. Here we'll use not LTK, we'll use limitizer that is suitable especially for Russian language. It's named biomorphy. You can also use, for example, PyMyStem, I guess, if I remember it right, or some other libraries. And so they are much better than using the standard from LTK. So it's again lematizer. And if we look on the words that are on the words after lemmatization, we can see that they are actually much closer to the words that exist in the language. So we can see, for example, that some verb after lemmatization also are verbs, but they're in normal form, not, for example, in past tense, like here. We can see also some nouns that are in multiple form, and then it goes to not sure how it is in English. I'm sorry. I'm not a linguist, so I'm not sure about some words in English. But it can be seen that normalization can transform all the words to the words that exist in language. So probably in some cases it's better. And if we take again the same sentence that we used in stemming, we can also see that sentence is much better than we have it in stemming. But actually, probably for some algorithms, it's not very important. For example, if we just want to calculate the number of some words, then it's not important how much they're degraded. So we can use stemming also in Russian. But here we'll use, for our task, we'll use lemmatization again. So let's run it through all our data. And also save it in some file. We can see, for example, the first text, and it will be like this. So again, we remember that we split our text to some tokens. We removed some punctuation, all stop words, and transform it using lemmatization. And we will have the text like this. So just not a text, it's just a set of words, but they were transformed to some normal form. So there won't be so many forms of words that have closer meaning. Okay, let's actually transform our words to some vectors. To do it, we will use a technique that named bag of words model. But firstly, we will split our data to training test part. And firstly, at first we'll use just two classes. So we will say that we have binary classification. So we'll say that we have a positive class and do some other that will name label it as zero class. And if we use bag of words model, we will what we try to do. We try to say that we encode our words as the number of words in the text. So, for example, if we have a sentence like this, after splitting it to words, we can see that some words they are more frequently can be seen in text. For example, the word movies, there are in two places, and some other words are just in one places, for example, like this. And if we encode our words with the number of them in the text, we can have vectors like this. And for the second sentence, we can also do the same thing. Here we can see that all the words have don't have repeatings, and we have encoding like this. So and we can see that there's some zeros here, and we don't have it here. It's because we said that we have a common vocabulary for both the centers. So don't words like, for example, I guess movies in the second sentence, so there will be 0. So in this manner, we will have some encoding for our sentences or for our words. We can have another example. For example, if we have 5 sentences like this, and if we took all the words, we can have this encoding. So, for example, word cat is only in one sentence, so one will be only here. And on the other hand, the word is in all texts, and in some places it are also some repeatings. But actually, the words like is or a that are too common for all the text are actually stop words, and in our text we will remove them, so it won't be a problem. So we'll have more values like this when we have in some places ones, but mostly we'll have zeros. And in Scalon, we have a function named configurizer that will do this encoding. So we'll say that we have actually 50 features. So we'll just have 50 words that we'll took from our dataset, and we will encode our sentences with these 50 words. And if we look on our top words, we can see that actually the first of them is a number. I hope it names something important, but we don't know actually. Also, we can see that actually we can see that probably this text is about the text is about some places in Russia. Okay, so if we apply this configurizer to our text, we'll get some vectors. So they have the length of 50. And for example, this is encoding for the first text. So we can see that in some places we have different numbers in all the places. Although we have only 50 words, we don't. So we probably not calculated all the words in all the texts. So probably this encoding is a bit too poor, but we will see it sometime. So we'll try to use logistic regression for our classification. We can, for example, remember what it is. So it's actually like in linear regression, but here we not just use our weights like this, we also apply after our linear model a sigmoid. So in our classifier, we'll return some probabilities for the first class. And also, I'm not sure what we should say here. We can just remember that we here optimize negative log likelihood. But actually, we will use just the ready function, logistic regression from Scalon. So we will feed it, predict, get some predictions. It also will have we will predict not only our targets, we also will return their probabilities, since for metrics it's better to for some metrics it's better to use probabilities and not just predictions. For example, for ROHAUK, since our plots will be more smooth for ROHAUK, and also we can have a bit better results. And also our probabilities are more flexible than just targets, since our targets will be just zeros or ones, and probabilities have range from 0 to 1. So they are more, they can show more to our metrics, and we'll get better, more meaningful results. So if you calculate our metrics, we will see that we have not so bad result. But if we look on our confusion metrics, we can see that actually there are some problems on the right. So here we have our, as I remember, we have true values here. So we have so here are true negative values. Okay, the values that are negative in our data, and here we have positive examples from our data, and here are our predictions. So we can see that we poorly predict positive class actually, and most of the examples we predict as negative class. So probably this we have an unbalanced problem. I guess we can look for the number of examples in both classes, but I don't remember where it was actually. Oh, okay. You can see. We said that we have in positive class we have positive sentiments, and other two are in negative class, I guess. So we can clearly see that it's an unbalanced problem. So probably we need to say, so we probably need to use some technique for balancing our classes, or probably we can just say to our logistic regression that we should balance our class weights. So we have this parameter, and we can say that it should be balanced. Here we use grid search. Just search through some parameters that we push to our logistic regression. So we have what we pass to grid search. We pass here logistic regression here, and we pass some parameters, and we pass it here. And we also say that we'll try balancing class weights and also without weights. We'll use different penalties. So we'll try different types of regression, and we'll measure also F1 score here. So, and actually it's better than just measuring precision or just recall, since F1 measure can measure them both actually, but a bit something like in so it's actually just a bit better metric for optimization, since it can say more about our confusion metrics and about our results. So we'll try to choose the best model with some parameters from the list using grid search, and our grid search will return our best parameters, and we can see that they are like this. And we can see that all the metrics are a bit better. So they were like this, and here, like here. Actually, we can see that row hook is the same, but our metrics like precision and recall are a bit better. And also, if you look on confusion metrics, we can see that after balancing our classes, we can predict results a bit better. So it's very good. Also, we can choose another number of features in count factorizer. So if we use more words for encoding our text, we can have a bit better results. So we'll try here different number of words, and we'll look on the results. So if we use just 100 words, we have a very close picture. But if we use, for example, words like this, we have much better result. So we have a better row count, F1 measure, and so on than what we had. If we use a bit more words, we can see that results are not very different. So I guess it's too much. And also we should remember that the more words that we use in our model, the bigger will be our vectors. So it should be harder to work with them, and it will be longer. So it's not good. So we need to choose the best number of the words, and also we should get the best results. So if we plot our results, if we plot our results, and also we have here a logarithm of number of our words, you can see that firstly our metrics are much better, and then they are not. So we can stop, for example, here and get, I guess this number of words, and we'll have very good results and not so much words in our model. We can also use grid search for all number of words, and we'll probably get even better results. Then we'll use another technique. We can not only use count factorizer, we can use TF-EDF. Actually, it's also about counting the number of words, but here we'll use, but it's a bit more smart technique. Here we calculate two things. Firstly, we calculate the number of some word in some document. Document here is just some news text. So we'll create a number of every word in every document. We'll have some matrix. It named actually term frequency or TF. And another thing that we'll calculate, it's inverse document frequency. Actually, it's the number of documents that in which we have this word. So again, we have some matrix, but here we calculate not document frequency, but inverse document frequency. And also we take a logarithm, since we can have a bit too big values here. So it's like this, and then we multiply TF and IDF, and we have some smart characteristic for our words, for frequencies of words. So we try to at first we try to do both things. we try to find the words that are frequent, but also we try to not use the words that are too frequent. Again, it's something similar to removing stop words. And these words will be most important. They will encode our text. So if we use df/adf vectorizer from Scalon, if we also set a number of features, we'll also have some vectors after this transformation. So we'll have vectors like this. They will have a length of 100, yes. And we can see that they are now the numbers and vectors are not int, they are float. And if we pass df/adf to our logistic regression, we can have also rather good results. I guess it's even better than what we have for small number of features in count vectorizer. And if we again try different number of features as we do it previously, we can see that our quality of prediction also becomes better, better, and so on. So, but actually, if you look on the maximum number of words, you can see that actually ROCAUC is not this high as we had it in count vectorizer. So we have it like this here, and here we had it like this. So probably we had better results with count vectorizer. Probably it's because there are some, we just don't need to penalize our model much for frequent words. Probably there are markers for this text. And again, we can see that after using more words in our model, we have better results. And again, we can choose we should choose the best number of words for a model and not to use too much of them. We can again choose it by using this plot. Okay, let's you see we don't have a lot of time, so let's go to support vector machine. Let's quickly remember what it is. So the most simple case when we have just maximum margin classifier. So we just say that in logistic regression, we just split our data by some linear. But then we can use also, okay, not linear, but hyperplane if we use multi-dimensional, if we have multi-dimensional case. But also we can say that all our objects lays in some distance from our hyperplane. And if we use, if we find the maximal distance to this, to the closest points from our hyperplane, then we have some margin in which we don't have any points. I mean, ideally, but more often we'll have some points that can be separated with that can be easily separated. So this maximum margin classifier is not so good for this case, and we will need to use a bit softer thing, soft margin classifier. So here we just say that we that some points can lie in the other half of the field, so they can go in the wrong part, but actually we'll just say that these points are these points are some errors, but most of the points will be classified right. And for maximum margin classifier, we'll have so we just what we do, we say that we need to find the maximum margin that can separate our points. And how we do it, we make our model and we say that it should be greater than this margin. And of course, we need to look on the sign of this thing. So we can multiply it just by pi. And we'll have here if they are positive, it means that it's great place on one side of our hyperplane, and if it's negative, then it means that it lies in the other part of our hyperplane. So there will be actually in this formula, we have one formula, but it means two things, two cases when our examples are positive or negative. And for soft margin classifier, we have a very similar formula, but we also have these things. They just show that in some cases we don't have margin. We have actually some negative margin with some small coefficient. It just means that some examples were missed and they lies in the other half that they should be. And also we should remember that we can just not split our points with some linear things. We can use something more something non-linear. In this case, we'll have some non-linear features here, and it actually now will work with subartifactory machines, but actually it's very similar to what we had here. But now with SVM, we can work also with nonlinear cases, and it's actually the best thing about SVM. So now we'll use SVM. In Scalon, it named actually SVC as its subartifactory classification. So if you use it, if you use again the FDF factorizer and the same number of features, we'll have this result. So remember, it's a bit better than we had in logistic regression, but maybe I'm wrong. We can also run grid search and try different kernels for our SVM. Kernels are just a way to transform our space to some other. So we try to use some nonlinear boundaries, and to do it, we use these kernels. So we can have just linear kernel, so it's just the linear case, or we can use something more interesting like polynomial or RBF and so on. And we will try all of them. And research can look for the best results by again the metric F1 score. And after some time, we'll have results. We have them also really good. So local is here. F1, which is also rather good. And we have, of course, some not so good results, as we can see from confusion matrix. And again, I guess we have worse results than we have in common factorizer. And the last thing that we should discuss is actually multi-class classification. So for now, we just worked with binary cases, and actually for logistic regression, it's normal, since we can just so logistic regression is only about separating things to two parts. So we just have ones and zeros. Since we have our sigmoid that can't work with something more difficult. So to somehow work with multi-class classification, we can use some technique. For example, we can just, if we have, for example, 3 classes, we can just compare them. For example, we can compare them 1 with 1. So we just say that we separate at first 1 we see 2, the first class we see the second class, then the second we see the third, and the third we see 1. So we need to do several classifications, so it can be not so fast. And another thing that we can do, we can do 1 with C all. So we'll just, for example, classify 1 with C 2 and 3, 2 with C, sorry, 2 with C 1 and 3, and 3 with C 1 and 2. So also we have to do several classifications, but actually if we really want to use logistic regression, then it's we just need to do it, since we can't do anything more. But also we can say that if the number of classes is much more than only 3, then we have some problems. We need to do very much number of computations. Also, even if we use 1 with C1 technique, then if we have, for example, n classes, then we need to do, I guess, this number of classifications, and it looks not so good. But actually, it's sometimes it can be better than 1 with all, since we don't need to train our model on all data set, but we just took separate classes, and in 1 with all case we work with all the data set. So it also, in sometimes it can be better to use 1 with 1 approach, not 1 with all, since all the classifications will take not so much time than 1 with all approach, despite their number. So if again split our training test, but now for 3 classes, and use again our TF IDF factorizer, we can use our 2 new classifiers. At first 1 with rest, and then 1 with 1. And again we run research to find the best parameters. So we can see that actually F1 score is similar for the strategies, So we can use them. But also you can see that F1 score is not so big as it was for binary problems, since we have more classes and it's harder to separate them. And for SVM, we don't have this problem. We can just use it. And after running it on our data, we can have, I guess, a bit better results. Yes. We can have the score, and we can see that we used polynomial kernel. So if you use nonlinear classifier, it's more suitable for our case. Then just using plain logistic regression. But actually, in practice, I didn't often see this 1VC rest and 1VC1 classifiers, but it's important to understand how they work. So I guess it's all that I wanted to say today. If you have some questions, then you can ask now, I guess. Okay, then goodbye. Have a good day.